Hi, everyone, and welcome to the ITCS 2023 talk on Extremal Combinatorics, Iterated Pigeonhole Arguments, and Generalizations of PPP. My name is Amol Pasarkar, and this is joint work with Christos, Papadimitriou, and Mihalis Yannakakis at Columbia University. So I'd like to start by emphasizing that in this talk, we will primarily be concerned with search, also known as function problems, where the objective is to search for a certain certificate, as opposed to simply decide whether or not the certificate exists, as we would in a decision problem. The major function problem classes include FP and FNP, and these are the search analogs of the more widely known decision classes, P and NP. Here, F in FP and FNP stands for function. The TF in TFNP stands for total function problems. The word total here signifies that these problems are guaranteed to have a solution. The NP in TFNP signifies that these solutions are also polynomially verifiable. And to make this formal, we can say that any TFNP problem is given by a polynomially computable relation R, and this relation takes as input x and y. Here, the x is going to denote the problem instance, and the y is going to denote the certificate. And the key property of totality with R is that for any x, any problem instance, there exists a y, which is a certificate, such that x comma y belongs to the relation. And the actual TFNP problem in this case can then be articulated as follows. You're given an input x, and the task is to find a y such that x comma y belongs to the relation R. Now, an interesting motivation for studying TFNP comes from the following dilemma. On one hand, there are problems in TFNP for which we strongly believe that there's no polynomial time algorithm. In other words, we believe these problems are not in P. One classic example of this would be the problem of factoring. On the other hand, we can appeal to the theory of NP, or in this case, FNP-completeness, to provide evidence that these problems are not in P. And the reason for this is if any of these TFNP problems actually were FNP-complete, it would imply that NP is equal to co-NP. So to address this, we need to actually introduce intermediate complexity classes that are in between FP and FNP, and these are the so-called FNP intermediate complexity classes, as you see in this figure here. And these intermediate classes are going to be used to characterize the difficulty of many of the problems in TFNP. So to build on that, while it's extremely unlikely that we would have TFNP complete problems, there are many notable subclasses of TFNP. And there's a very subtle point to consider here, that the problems in TFNP are by definition total, and this means that there should be a mathematical proof of totality. But note, if the mathematical proof was constructive, that is, if it describes a procedure for generating the certificate for a problem, then we can simply follow that procedure in an algorithmic way and efficiently find the certificate in polynomial time. This would place the problem in FP, but we believe a lot of these problems are not in FP, and the hardness of these problems in TFNP comes from the fact that the mathematical proofs of totality are actually non-constructive. That is, they don't show you how to actually construct the certificate, at least in an efficient way. And in line with this, Papadimitriou, Johnson, Yannakakis, and others in the 90s sought to organize the problems in TFNP based on their mathematical proofs of totality. And each subclass of TFNP embodies one of these mathematical proof methods. So here are some examples. The class PPP embodies the Pigeonhole principle, and we're going to talk about this in great depth shortly. The classes PPA and PPAD embody a combinatorial principle, which we'll call the handshaking lemma. And the class PLS captures the challenge from optimization of finding local optima. And in this talk, we're actually going to introduce a new class in the TFNP world, which we're going to call PLC, which stands for polynomial long choice. And this class embodies a similar but more expressive argument than PPP, which we'll call the iterated pigeonhole principle. So as we're interested in the pigeonhole principle, a natural starting point then is to discuss the class PPP, which stands for polynomial pigeonhole principle. This class is defined in terms of its complete problem, pigeonhole circuit, and in some papers you're going to hear this problem called collision. And in this problem, you're given a polynomial in n size circuit, which maps the integers from 0 to 2 to the n minus 1, and this is typically given by a set of n-bit strings, so they're represented efficiently, and it's going to map this set to itself. And the challenge is that you either want to find an element that maps to 0, an x such that p of x is 0, or you want to find a collision. And it's straightforward to see that this problem has to be total because on one hand, if you have a zero element, then you're done, you have a certificate. But if you suppose instead that there are no zero elements, that is, there's no element x such that p of x is equal to 0, what this in turn tells you is that every single element in the domain of p is actually mapped to a value in the range 1 through 2 to the n minus 1. To make that more concrete, that means that there's 2 to the n elements in the domain that are being mapped to a set of size 2 to the n minus 1. And by the Pigeonhole principle, there has to be a collision. So we then define the class of problems that are polynomially reducible to a Pigeonhole circuit as the class PPP. And of course, I'd like to emphasize that this problem is hard because the function is represented concisely by a polynomial in n circuit, whereas the search space is actually exponential in n. Of course, if we're given an explicit representation whose size matches the size of the domain, then the problem would be in P. And to see why, we could then check every combination of inputs until we found a zero element, and we could do that in polynomial time, or a zero element or a collision, to be clear. So interestingly, the Pigeonhole principle that we just talked about is just one counting argument in the much broader field of extremal combinatorics. And the ideas in extremal combinatorics typically encapsulate the following general phenomena: that if a collection of objects becomes large enough, there has to be some structure that exists. And with regards to TFNP, we're going to focus on 3 themes and the corresponding lemmas in extremal combinatorics. Each lemma gives rise to a corresponding TFNP search problem, as we're going to see. So first, we're going to look at problems whose totality is based on an iterated Pigeonhole principle argument. And these are the problems which belong to the class PLC. The underlying lemmas include the sunflower lemma as well as Ramsey type theorems. Second, we're going to introduce new problems which are PPP complete. And this includes problems based on König's lemma and the Erdős-Corrado lemma. And third, we're going to consider problems that are harder than PPP because of the way in which they're encoded. And in this setting, we're going to consider problems based on Turan type theorems. So without further ado, we're going to start by discussing problems involving an iterated Pigeonhole principle argument. So we're going to start by introducing this game that we'll refer to throughout this talk. And this is a really interesting 2-player game. And in this game, we're going to start with 2 to the n pigeons. And player 1 is going to start by picking a single pigeon. This choice can be arbitrary. And it's going to leave 2 to the n minus pigeons left in the game. And at each round, player 2 is going to partition the remaining pigeons in the game into 2 groups. And player 1 is then faced with a choice. Player 1 has to pick a pigeon from one of these groups. And upon doing so, player 2 is going to remove the pigeons from the other group entirely from this game. So at every round, there's going to be some set of pigeons that are going to be removed from the game. And the game ends when there's no more choices that player 1 can possibly make. So if we want to think about the objectives in this game, player 1 has the objective, player 1 wants to play this game for as many rounds as possible. In other words, player 1 wants to pick a long sequence of pigeons, whereas player 2 actually wants to make this impossible. And player 2 is going to partition the pigeons at every single stage in such a way that player 1's options diminish as rapidly as possible. So the question then becomes, what's the optimal strategy for player 1? And it turns out that there's an optimal strategy wherein at every round, player 1 picks a pigeon from the larger majority side of this partition that player 2 creates. And by doing this, player 1 is guaranteed to pick up to n plus 1 different pigeons. To see why, we just apply the Pigeonhole principle at every stage. And we can use the bound induced by the Pigeonhole principle to argue that so long as player 1 is picking from the majority, there's going to be a certain amount of pigeons left, and we can continue this argument for n stages to get to a final result of n plus 1 pigeons. So we're going to call the argument that's used here the iterated majority argument. So we can turn this game into a TFNP search problem if we equip player 2 with a suite of polynomial time algorithms, and these are adaptive algorithms. And the challenge is to successfully generate a sequence of length n plus 1 as player 1. And in fact, this is exactly how we're going to define the problem long choice. In long choice, the universe of objects corresponds to the pigeons, and the circuits, PI, represent player 2's algorithm at stage I of the game. Note that the circuit PI takes as input all of player 1's choices up to round I of the game. You can see this by noting that PI, the ith function, takes as input I plus 1 inputs, and the first I of these are the choices that player 1 has made up to this stage of the game. And you note that the circuit PI takes as a constant value. So essentially, the circuit PI takes this added restriction here that the sequence that we generate, PI has to be constant over this input for all AJ greater than AI. And this is an interesting kind of condition to enforce. But this condition really is trying to enforce the concept that player 1 can only pick from the remaining pigeons from our 2-player game. So the challenge, again, for player 1 is to generate this long sequence of objects from this universe. And we should take a pause at this point and think about why this problem is actually hard. After all, we did give a seemingly constructive procedure for player 1 to win the 2-player game that we described, and long choice is really just a formulation of that 2-player game. And a big challenge here is that estimating the majority of roughly 2 to the n elements, or estimating the majority at any stage of this game in poly n time is extremely hard. And the reason for that is because the number of available objects that you can use to continue this construction, in other words, the number of objects that player 1 can continue to add to this sequence diminishes rapidly if player 2 plays optimally. And as a result, it becomes hard to not only estimate the majority, but it also becomes hard to pick an element from this majority. And these are both things that player 1 has to successfully do to solve this problem. So again, the hardness here comes from the fact that the problem instance is represented concisely using circuits. And if we were given an explicit representation, this problem would be in P or FP. So we define the class PLC to be the set of problems reducible in polynomial time to long choice. And we note that the totality, again, entirely follows from the totality argument, the iterated majority argument that we just talked about. So thus far, we've discussed PLC and long choice, as well as PPP. And it seems that PLC captures this iterated majority argument, which involves a repeated and an adaptive use of the Pigeonhole principle. So then it shouldn't be too surprising that PPP is actually contained in the class PLC. And to prove this, we simply reduce the PPP-complete Pigeonhole circuit problem to the PLC-complete long choice problem. And to do so, we construct a universe for our long choice problem, which is just a domain of the circuit from the Pigeonhole circuit problem. And player 2, given by the functions PI, place restrictions of the following kind. They force any valid long choice sequence to have the property that later elements in the sequence have closer and closer images. And if we define the functions PI appropriately, then these functions guarantee that any long choice sequence is going to have the property that subsequent elements in the sequence are closer and closer together under their mappings via the Pigeonhole circuit. And by the time you get to the end of this long choice sequence, the elements are going to be so close together that they'll have to collide with at least one other element in the sequence. And that collision is going to give you a certificate to Pigeonhole circuit. Of course, to see the full proof, it's in the paper, but that's the general outline. And of course, I'd like to note that we think it's unlikely that PLC is equivalent to PPP for the same reasons we discussed, that there's an adaptive component and a majority estimation procedure that's not quite there in the more static PPP. So another combinatorial result whose proof uses the iterated majority argument is Ramsey's theorem. And the version of this theorem that we're going to discuss here is as follows. You have a complete graph of size r to the Rn, and you color each edge using one of R colors. There must be a monochromatic clique of size n, according to Ramsey's theorem, and there's an iterated majority argument at play here as well. So to sketch the beginning of this argument, we can repeat the following procedure up to Rn plus 1 times. You pick a random vertex, and then you partition the remaining vertices based on the color of their edge to this vertex. And by the Pigeonhole principle, there must be at least r to the Rn minus 1 vertices whose edges to this first node have the same color. And what we're going to do is we're going to keep all of those vertices and discard the rest. And then we're going to pick another vertex from the remaining set of vertices, and we're going to repeat the exact same procedure, starting with this second node. And we can repeat this procedure many times, and the resulting structure that we're going to construct in this process is going to be awfully similar to long choice, the long choice certificate, or this sequence of pigeons as we talked about. And the idea then is that you can take that structure, and then you can quickly use it to construct a clique. Essentially, that's the proof. And you can take the problem, the TFNP problem based off of this Ramsey's theorem, which is a graph essentially given implicitly by a circuit of polynomial size. And this circuit's going to take 2 nodes as input, and it's going to output the color of its edge. So this graph is going to implicitly define an edge coloring on the complete graph of size r to the Rn. And the challenge, of course, is to find a monochromatic clique of size n. And based on the proof of totality that I just described, we can actually use that proof to directly encode this problem as a long choice problem. So there's a pretty straightforward proof, essentially, that r comma n Ramsey reduces to long choice and therefore belongs to PLC. So another related result from extremal combinatorics is the sunflower lemma. To introduce this result, we should first look at some notation. We call a k-set system a collection of sets, all of which contain k elements. And in the figure on this slide, the rectangles here describe sets of size 3. So we can refer to them as a 3-set system. A sunflower is a collection of sets with the property then that every pair in the collection has the same exact intersection. And in the figure, you can see an example of a sunflower. These sets all contain the same value in common. All their pairwise intersections only contain the value 2. So this forms a sunflower. And the reason that we call this a sunflower is actually visual in nature. You can think of the common intersection going to the center of the sunflower, and the petals contain the disjoint components of each set. So for example, this set, 15, 5, and 2, the 2 goes to the center here, and the 15 and the 5 go to the petal. So the sunflower lemma is going to argue that a sufficiently large set system must have a sunflower. And it's important to note that the extremal bounds provided here are actually not the strongest known to date, in particular this bound here. In past years, there's been breakthrough work by Alweis and others that has significantly improved this extremal bound. However, we can still meaningfully work with these weaker bounds as they give rise to still provably hard TFNP problems, which I'll talk about in a moment. So we're going to formulate this problem naive sunflower here. And this has a weaker extremal bound than what we described in the previous slide, which is why we call it naive sunflower. And we note that this bound doesn't actually diminish the hardness of the problem. It's actually still hard. We can prove this under cryptographic assumptions, specifically under the assumption that collision-resistant hash functions exist. And in this problem, we're given a k-set system with k cubed times log k sets, and we'd like to find a sunflower of size k squared. This set system is given implicitly, as usual, by a poly k size circuit. And concretely, it's going to take as input an index, and it's going to output a corresponding element of the set system. So it's going to actually output a set of size k. So now we provide a detailed proof in the paper that naive sunflower reduces to long choice. And the key gadget in this proof is this result by Deza that describes how to characterize sunflower as a combinatorial structure as a collection of pairwise equidistant points in a metric space. And to do this, you can take any 2 sets and you can define a distance between them as the size of their symmetric set difference. This is a valid metric, and under this metric, sufficiently large sunflowers are equivalently characterized as collections of pairwise equidistant objects. And using this correspondence, we can then take a set system and we can convert it to a graph where every single node in the graph corresponds to one of these sets. And we color the edge between any 2 nodes based on the distance between the underlying sets that these nodes represent. And if we take this approach, a clique then corresponds to a collection of pairwise equidistant sets. And therefore, the problem of finding a clique allows us to find the sunflower. So this line of reasoning shows that naive sunflower actually belongs to PLC, since r comma n Ramsey belongs to PLC. So the reduction essentially takes naive sunflower, reduces it to r comma n Ramsey. In this case, it reduces it to square root of n comma n Ramsey. So r is equal to square root of n. And that problem then directly reduces to PLC. So we've shown that there are indeed interesting problems in PLC, all of PPP, Ramsey, and sunflower. And what we're going to consider here is a dual argument of PPP. And this gives rise to an empty pigeonhole principle argument. If I have a few pigeons and many more pigeonholes, no matter how I place the pigeons into a pigeonhole, there must be an empty pigeonhole. The search problem here is to find the empty pigeonhole. And this idea was first introduced in the work of Mitropolsky, Kortin, Kleinberg, and Papadimitriou. And they defined this problem empty, given here. It was very similar to pigeonhole circuit. The only difference is that this concisely represented circuit C maps a smaller input space to a larger range. In particular, it excludes the element 0 in the input space, but the element 0 is actually included in the output space here. So the challenge becomes to find an element in the output space that does not belong to the image of the input space. So certainly such a problem exists, which makes this total. And we define the class PEPP to be, or PEP, to be the set of problems polynomially reducible to this problem empty. The question then becomes, how do we know that such an empty pigeonhole exists? Unfortunately, it's not very clear how to polynomially verify that an empty pigeonhole is indeed an empty pigeonhole. The only way we'd know how to do so would be to actually check every single input and map the input through C, but doing so requires exponential time. So there's a kind of a quantification that's at work here. And this problem actually belongs, it's a total problem that belongs to the polynomial hierarchy TF sigma 2p. So in the same way that PEPP is a dual argument of PPP, we can consider also a dual argument of long choice. And we define a problem, which we call short choice, and it embodies this dual argument where if we recall the two-player game from the beginning of this talk, player 1 wants to pick as many pigeons as possible in that game, and therefore player 1 is going to pick from the majority. If instead player 1 wants to terminate the game as quickly as possible, they can actually repeatedly choose from the minority. And this argument is called an iterated minority argument. And the short choice problem encapsulates this challenge. We're given a standard long choice problem, but with slightly fewer elements, in particular 2 to the n minus 2 elements in the universe. Our goal is to find a short sequence, then, which cannot be extended. That is some sequence of elements a0 through ak with the property that they satisfy the conditions from long choice imposed by the functions pi, but we can't extend this sequence in one direction, either 0 or 1. And the challenge is to find both that direction as well as this sequence. And the totality follows from this iterated minority argument that I just described. So accordingly, we can define the class PSC, polynomial short choice, as a set of all search problems that are polynomial time reducible to short choice. And in the same way that PLC is more expressive than PPP, we can use a similar dual proof to show that short choice is actually PEPP hard. And in that sense, PEPP is included in the class PSC. The open question then becomes, what are the natural problems that belong to this class PSC? Great, so thus far we've discussed problems which involve the use of the iterated pigeonhole principle, and now we're going to discuss other problems from extremal combinatorics, which are actually PPP complete. We'll start with Koenig's lemma on a binary tree, and this essentially states that if you have an infinite binary tree, there must exist an infinite simple path from the root of the tree. This seems like an obvious statement, but it's instructive to consider how the pigeonhole principle actually plays a role in proving this fact. So interestingly, the proof method closely follows the iterated arguments discussed thus far. We start at the root, and we note that at least one of the left or right sides of the binary tree contains infinitely many nodes by the pigeonhole principle. So we can proceed in that direction, and then we can repeat this argument on that subtree, and we can repeat this forever until we yield this infinite simple path. The König problem considers a finite or extremal case here, wherein we have a binary tree of size 2 to the n nodes, and we're asked to find either a simple path of length n plus 1 from the root, or to find a violation of the binary tree structure. I'll note that the proof of totality I just gave should suggest that the problem belongs to PLC, which it is. But Interestingly, the problem is actually PPP complete, and I'd encourage you to check the paper for the full details. Another result which we consider in this work is the Erdős-Korada lemma from extremal set theory. And as with the sunflower lemma, in this setting, we're considering k-set systems. However, the question is slightly different. It is how large can a k-set system with the constraint, can a k-set system be, with the constraint that every pair of sets has a non-empty intersection. So the Erdős-Korada lemma states that if the universe has more than n-1 choose k-1 sets, where n is the size of the universe, there must be two disjoint sets. And we can correspondingly formulate a TFNP search problem as follows. Given a k-set system consisting of more than n-1 choose k-1 sets, the problem is to find two disjoint sets if they exist, or if they don't exist, there must be a violation of some kind. The problem must be ill-formed. In particular, there should be either, for example, two identical sets or an invalid coding of a set. And an important detail to keep in mind here is that this problem, again, as we've seen with TFNP, it amplifies the hardness by changing the size of the universe to be exponential in the size of the problem representation, which is poly m. So this is something that we've seen with all the other problems, and this is exactly the same construction here. And of course, in this problem, we've simplified where k is actually equal to 2 here. So what we find is that if we have a circuit that is able to generate this collection of k-sets, then this problem, Erdős-Korada, is actually PPP complete. Great. Now we're going to discuss a class of problems which define hierarchies that go beyond PPP, and their source of hardness arises in a sort of from the indirect way in which the problems encode the problem instance. So we're going to start with discussing a kind of yet another flavor of graph problems, which I'll refer to as Theorem type problems. And we're going to start with a simple case of this, Mantel's theorem, which states that any triangle-free graph of n vertices can have at most n squared over 4 edges. And to understand this extremal threshold of n squared over 4, it's useful to consider the case where you have a complete bipartite graph of n over 2 vertices on each side. That is, you have n over 2 vertices on each side of the bipartition, and you generate every single allowed edge between these two groups of vertices. That gives you n squared over 4 edges. Now, Theorem's theorem addresses the more general question of how many edges can a k+1 click free graph have? Rather, how many edges can a graph have while simultaneously being free of clicks of size k+1? And Mantel's theorem refers to the special case of k equals 2, of course. And the extremal case here is pretty similar to Mantel's theorem. We're going to consider a complete k-partite graph with n over k vertices in each partition. And to generate all edges in this k partition, the way you can think about this is there are k choose 2 ways to pick 2 partitions. And then once you pick these 2 partitions, there are n over k squared edges that you can generate between the nodes in these 2 sides of the partition. And therefore, k choose 2 times n over k squared is kind of the expression that you get for the maximum number of edges you can generate in this setting. So we can formulate a search problem that is structured as follows. If you cross this extremal bound that I just described, then there must be a click or there must be some related violation. And as usual, we're going to consider implicitly represented graphs. So instead of considering n vertices, we're going to consider 2 to the n vertices, or other graphs of size 2 to the n vertices. And the problem is going to essentially say that you have this efficient circuit, or this efficiently represented circuit, and it defines k choose 2 times 2 to the n squared plus 1 edges. And this is a graph of k times 2 to the n vertices. So this expression exactly mirrors the extremal bound that I just described. And we're going to cross that extremal bound by adding 1 extra edge. And the way this circuit functions, just to be clear, is it has an input, concise index, and the output is going to simply be a pair of vertices each vertex is represented by the logarithm of this, so n plus log k bits. And the challenge is, again, to find a clique or to find some invalid formulation of this problem. This is essential to keep the problem total. So what we find is really interesting is that PPP reduces to 2 Taran, and then there's also a hierarchy where every successive value of k is kind of a more general version of this problem. So k Taran reduces to k plus 1 Taran for all k greater than or equal to 2. And we believe that this problem is harder than, these problems are all harder than PPP, and they're harder than each other because at each successive stage of this hierarchy, there's a more and more indirect encoding of the problem instance. And that indirect encoding for information theoretic reasons makes the problem harder than PPP. Great. So this work raises many interesting questions, some of which we'll list here. We've considered this large class of TFNP search problems from extremal combinatorics, and many of these problems inspire the definition of new classes like PLC and PSC. And intuitively, it seems that PLC and PSC are significantly more expressive than PPP and PEPP. However, it would be interesting to see these black box separations that actually provide further evidence of this separation and hardness. And it would also be very interesting to see more natural complete problems for these classes. And finally, as mentioned, we've considered a variety of extremal problems here, but the hardness of the TFNP problem is connected with the strength of the extremal bound. So it'd be interesting to see further analyses of TFNP problems that have stronger extremal bounds. Great. And thank you so much for listening.